Well, I can't seem to hide that annoying panel, but we'll get started. There's like a switch over there that you can turn off the lights. Yeah, we have lights on. Yeah. Anything else? Yeah, perfect. Okay, so today's lecture and general this week. Sorry, I can't seem to hide that. I don't know if anybody remembers the key combination, then I hide it for the panel. Right now, I can't even find it. Well, let's try. There. Okay. Okay. Very good. Okay. So our topics as shown here, we're going to talk about Maxwell's equations and electromagnetic waves. We've kind of put the geometrical or ray optics part of the course behind us from last week, and now we are moving on to waves. And in particular, we're going to understand or talk about a property of electromagnetic waves that is different from most waves that you have encountered in normal everyday experience. So usually we think about water waves or we think about like sound waves. There's one aspect of electromagnetic waves or light that's very different from those waves, which is that it's a vector. We'll discuss that in this next two lectures. Okay, so to begin with, I'm showing you the Maxwell's equations. So there are two sets of equations, there are two classes of equations out of the four. The first class is the divergence equations, which go as del dot D equals rho, del dot B equals 0, where D is the electric flux density, E is the electric field vector, and rho is the charge density. B is the magnetic flux density, H is the magnetic field vector, and J is the current density. And then we have the curl equations, which is del cross E equals minus dou B over dou T, del cross H equals dou D over dou T plus J. Now, can I ask, how many of you have seen Maxwell's equations in this form? Couple of you. Okay, a few of you. All right. Don't worry, we'll talk a little bit more in detail about it here, but obviously this I can't go into too much detail because this isn't a course about electromagnetism, but we will discuss it from the perspective of things that you already know, such as Coulomb's law, right? So you already all know that if you have two charges and they're at the vectors, position vectors R1 and R2, there's a force between them, which is this F12 or F21 acting on each individual charge. So F12 is a force on 2 due to 1, okay? And F21 is a force on 1 due to 2. Okay, so here it is. And that is just given by Q1, Q2 divided by 4 pi epsilon R squared. And you've all seen this, so I'm not going to talk about it in detail. Just R is the vector which is pointing from the point P1 to the point P2. So this is Coulomb's law. From this, we can derive the Gauss's law, okay? And that's the first equation. So how do we derive that? Well, we start first with a single point charge, which is acting on some point P, which is at the position XYZ, and we introduce the electric field, okay? Instead of the force, we say that if there was a test charge over here at this point P, it would experience a force which is given by Q, the test charge, times EP, where E is the electric field. So that's the force per unit charge, and this you're all familiar from your first or second year electromagnetism. And if we now make this source charge, the charge that's responsible for the electric field at the point P, if we make that a continuous charge distribution, then we can take some small volume in that continuous charge distribution, and which is at a point R prime, which is given by this R prime vector over here. And we can write down the electric field at the point P in the direction R, which is again on the line joining the point R prime, the source point, to wherever we are measuring the field. And the field is usually measured by putting like a test charge at that point P, okay? So EP is just now without the dividing by the test charge, Q, so that's just R times Q, where capital Q is the source charge. capital Q is the source charge divided by 4 pi epsilon r squared. I didn't say this, but epsilon might be not necessarily just the vacuum permittivity, but could include the effects of materials, like a dielectric material that's surrounding everything. So we allow it to be, in general, epsilon, which we'll come back to in a little bit. Okay, so that is our electric field. And now, if I want to add up all the contributions from the various elements of this continuous charge distribution, we write down the charge Q as a small element dQ, and that dQ is just given by the charge density rho r prime times dV prime, V prime, dV prime being a volume element. Okay, so that's the volume element dV prime. So now again, the electric field at the point P is given by dEP equals this term, just replacing Q by rho times dV prime. And now the total electric field at point P due to all of the charge is simply that integral over the entire volume V of this R of this expression. Okay, so hopefully this all is familiar to you from earlier courses. Now what we want to do is derive the Gauss's law from this, which also I'm sure you've seen, which is that we introduce a quantity called the electric flux density or the electric displacement. And this electric displacement is simply epsilon times the electric field. Okay, so this epsilon times electric field, and if I now take any point on a spherical surface of radius r, which is centered around this an isolated point charge. So I'm just taking a single point charge again. So d is equal to r times q over, now because the epsilon is multiplying e, I get 4 pi r squared. Okay. So this is the picture of the situation. There's an isolated point charge, and then I take a spherical surface of radius r, which is centered on that charge. Therefore, we can write that the integral of d on that surface, the spherical surface, which is the flux, d dot ds, right, which is the number of flux lines that are emerging from that surface or going into the surface, that's the sum of all the flux lines. Then that's equal to Q divided by 4 pi r squared times the surface area, because the field or the electric displacement is a constant all along this surface, and it's pointing outward from this isolated point charge. So we get equal to Q, and this is true for any surface enclosing the charge. That is, of course, the proof. I'm not going into that. That is the Gauss's law proof. So that is just showing that any charge or any surface integral or any area surrounding this point charge Q must have the same flux. D dot dA must be equal to, or D dot ds, sorry, must be equal to Q. Okay. Now we apply step 2 of the emissions. Okay, so that is the integral form of Coulomb's law or Gauss's law. And now we can convert that to a superposition of like a volume distribution. So if instead of having a point charge Q, I had some volume of charges, continuous charge distribution. Again, I can replace the total Q by simply the integral over the volume of that source distribution, which is integral V times rho dV. Okay, so that capital Q, I just replace again by this integral over the volume rho dV. Now this is over the source charges. Okay, and now I apply the Gauss's divergence theorem, which says that the integral over the flux over an area is equal to the divergence of that vector times the volume integral, or it's a volume integral of the divergence. Okay, so this divergence theorem is from vector analysis or vector calculus. So it's true for all vector fields, F, where F is any arbitrary vector field. Then we can apply this equation 115 to this equation 114. So integral over the surface d dot dA is simply integral over the volume del dot d dV. And on the right hand side, I have integral over the volume rho dV. So I equate that to the right hand side, rho dV. And now I can just equate the two individual integrands over there, because this must be true for all volumes. And therefore, we have Gauss's law for electromagnetism, which is del dot D equals rho. Okay. This you may have seen in another way as del dot E equals rho divided by epsilon naught. So for vacuum permittivity or vacuum, whenever in a vacuum, then D is simply epsilon naught times E. So you might have seen this written as del dot E equals rho divided by epsilon naught. Okay. Okay, so that's the the electric flux density, or del dot D equals rho. That's the first equation in the Maxwell's equation. The magnetic flux density, the same expression. If you think about what happens to the magnetic flux, well, we can ask ourselves what happens as you successively divide a bar magnet. Well, as you know, when I take a bar magnet, which is of course the source of the magnetic flux or the magnetic field lines, and I try to divide that. Well, what happens is I also end up with north and south poles on both sides. Okay, so instead of being able to separate this as a north and a south separately, I always end up with this combination north south, north south. Okay, so and you can keep doing that down to the smallest elements, and you still always will get this combination, a north south or a dipole type of magnetic field. You can never get a monopole magnetic field. Okay, which I'm sure you all heard about this, that there are no isolated magnetic monopoles in nature that we have found. Okay, so by the exact same arguments that we just carried out for the electric field, if we carried out the same arguments, because we can always find the surface that encloses that dipole, the total magnetic charge inside that dipole, inside that surface must be zero, because there's a positive and a negative magnetic charge, so they cancel out. So by that same argument, the magnetic flux lines basically must always enclose back on themselves. So the net number of flux lines from any volume element must be zero. Okay, and therefore that gives us again integral over this over a surface is B dot dA. B is the magnetic flux density, and that gives us del dot B equals zero. Again, by just applying Gauss's divergence theorem, we can simply say del dot B must therefore be equal to zero. Okay, so that gives me the second divergence equation in Maxwell's equations. The third equation in Maxwell's equations comes from Faraday's law. Okay, so Faraday's law, as you know, states that, and you've seen these experiments performed, I'm sure, where you take a loop of wire, okay, and you connect it to a galvanometer or some other situation where you can read the current or the voltage across that, and then you move a magnet in close to that wire. And you can do the opposite thing as well. You can change the current going through it, etc. You can do lots of different things, but the point is, as soon as you move a magnetic field or change the magnetic flux through that loop of wire, then basically you get an electric field, or essentially a voltage across, an induced voltage across that wire, which causes current to flow usually. And when you write that down as in this form, which is the induced voltage is the negative because it always opposes the change in this flux. The changing flux gives rise to induced voltage across the terminals of this loop, this contour or the circuit C. Okay, and psi, as I said, is the magnetic flux that goes through or links that closed loop C. And I'm sure you've all seen this many times in your initial courses. So now psi, of course, which is magnetic flux, is simply again the area integral over the surface area of that loop, which is in this case that surface area can be anything. You can see I can draw a surface that encloses the loop, and on which the loop is sort of like, like think of a balloon, expanding with a fixed contour around that fixed loop. I can make a balloon that expands around it, and all of that surface could be my surface for the integral S B dot ds. Of course, the smallest surface I could imagine making is simply imagine like a soap film that's stretched across that contour, that loop. That would be the smallest sort of surface, and that's certainly one surface, but any surface that basically encloses that loop is allowed in this calculation of the flux. Okay, and the point is, S is the area of the surface enclosed by the contour C, and the induced voltage now V induced can be expressed, of course, as the line integral of the electric field around that contour. So that's the induced voltage. This is just familiar to you from the definition of potential and potential energy. So that's just the induced voltage is just the line integral of E dot dl. So that's E is now the induced electric field. So we can now write Faraday's law, which is this expression 120, in this form, which is integral over the contour E dot dl is minus dou over dou t B dot ds. So that's the integral form of Faraday's law. Okay. Now we will again cast this into a differential form. Okay. And the way we do that is we use a famous theorem again from vector calculus, which is called Stokes' theorem. Okay. And that introduces something called the curl. Hopefully you've heard about the curl or seen the curl of a vector field. So you can have a curl. Obviously, one simple example might be, think about like water, which is draining down a hole and it sort of circulates around that hole. So if you have vector field lines circulating in some area, that's going to give you a vector circulation, and that the curl will be positive. There are other ways also. You can just have the vectors increasing in length in one direction or decreasing in length in another direction, etc. That also will give you a curl. Okay. But anyway, those are some examples of how you can have a curl. And so again, we use the Stokes theorem, which says the curl of a vector field on a surface, which is enclosing a contour C, gives you the line integral around that contour. So applying that to that earlier integral form gives me del cross E now must be equal to minus dou B over dou T. Okay. So we combine, basically this 1.24 with that earlier, with just the equation that I just put on the earlier slide. Okay, so this is the point form or the differential form of the Faraday's law. Okay, and the last sort of law that you're all also familiar with is Ampere's circuital law, which predicts how much magnetic field there is when you have a current in a region. Okay, so as you know, a steady current will give rise to a magnetic field, and this steady current, for example, in a wire, gives rise to a magnetic field that's circulating around that wire. Okay, and that circulating magnetic field can be written using Ampere's circuital law as integral of around the contour, that is in which the wire is piercing through that contour in this case, or through the surface that is enclosed by that contour. So any surface that encloses that contour, if I calculate the current density through that and integrate surface, take a surface integral of that J, the current density on that surface, which is equal to then the total current going through that surface, that is equal to this circulation or the integral of H dot dl. Again, I apply that Stokes theorem, which is again in this form. So I write integral over the contour F dot dl, which is here integral over the contour H dot dl, must be written as del cross H dot ds. And therefore, I get now del cross H equals J. Okay, and this is what Ampere's law was until Maxwell came out. Okay, Maxwell spotted that there was a certain asymmetry between this law and the Faraday's law that I wrote down for you earlier. Okay, the Faraday's law showed that a changing magnetic field causes an electric field. Del cross E equals minus dou B over dou T. But in this expression, which says del cross H is equal to just J, there's no term that relates it to the electric field. So he spotted that there was an asymmetry in these equations, and he believed there must be a symmetry element, and he understood how to do that. He came up with a thought experiment which said that indeed, when there's a changing electric field, there must also be a magnetic field. I'm not going to go through that thought experiment. I'm just going to point out that there's one other equation. Whenever we have a time varying situation, the charge conservation is given by something called the equation of continuity, which says that the current that is in a medium, in an area, the change in the current across that area or something like that must be equal to the rate of flow of the charge that goes out of that area. Okay, so the spatial gradient or the divergence of the current density must be equal to how much charge is leaving that particular volume. Okay, and you can convince yourself of this by taking some volume and calculating the divergence of the current, and you'll see that it must be equal to the total charge that is flowing out of that current, out of that volume. Okay, so from this equation of continuity, which is del dot J equals minus dou rho over dou T, we see that if we now take the divergence of this term over here, so we take divergence on both sides, we have del dot del cross H on the left-hand side, and on the right-hand side, we have del dot J. Well, again, by vector calculus, we know del dot del cross H is 0. Okay, that's guaranteed, okay, for any vector field. But obviously, del dot J does not have to be 0. So we need a term here to guarantee that this identity is satisfied. So we add in the term that del dot J plus dou rho over dou T, which is guaranteed to be 0 by charge conservation. Okay, so this is not how Maxwell originally derived the equation, but it's enough for us to understand why this term must exist. Okay, And okay, so to make the equations consistent, we see that we have to add in this extra term. So we have, therefore, del cross H. And now we can use Gauss's law, that is, we can write del dot J plus dou rho over dou T. Well, rho is simply del dot D from Gauss's law. So this entire thing can be written as del dot J plus dou D over dou T. Okay. And so therefore, to equate these two sides, these two terms being equal, we must have del cross H is J plus dou D over dou T, which says that a changing electric field, remember D is just the electric displacement, must also give rise to a circulating magnetic field. So that's the symmetry of all the equations or the symmetry between the equation for the Faraday's law and the Ampere's law that comes above. Okay. So to summarize then, Maxwell's equations, as I said, can be written in two categories. One is the divergence equations, which essentially says that the flux lines for the electric field will start and end at a charge, either an isolated charge, while for poles, it means that they must always enclose a region where the flux lines are always going to start and end inside that region. There's no net flux. Okay, and on this side, as I've just said, the changing magnetic flux or changing electric flux gives rise to the field of the other type. So changing electric flux gives rise to a magnetic field, and changing magnetic flux gives rise to an electric field. Okay. All right, so that is the Maxwell's equations summarized. And now what we want to do is apply this to a certain category of materials. So of course, we can apply this in vacuum. So in vacuum, these equations are clearly going to just be satisfied with like epsilon replaced by epsilon naught, and mu, which is the relationship between the H, the H is related to mu by a term which I'll just introduce right now. Okay. So the point I'm trying to make here is that not only in the vacuum, but also in certain types of materials, which we call linear materials, these equations become quite easy or simplified enough to solve quite easily. And those are typically all the materials that we are going to consider in this course. Okay. And these materials, which are linear materials, are such that D and H, the displacement and the magnetic field, are related to E and B, the electric field, and the B, the magnetic flux density. Okay. So there are no higher powers in these materials of these field values. Okay. So for example, in linear dielectrics, like any normal materials that we normally encounter, like water or glass, etc., and assuming that these materials are isotropic, we'll see there are certain types of material that are not isotropic, meaning the permittivity can be different in different directions. Okay, isotropic means it's the same in all directions. We'll see there are certain classes of materials that they're not, and we'll understand how that works in a bit. But most of the time, we are looking at isotropic and homogeneous media, like water or glass, or etc., air, gases. All of these are typically can be just assumed to be isotropic and homogeneous. We can assume the permittivity is constant throughout the medium and in every direction. And as I've just summarized over here, many common materials are in this category. And let me just finish. Similarly, we can take linear isotropic homogeneous magnetic materials. Then B equals mu naught H plus a term, which is the magnetic polarization, similar to how we have D equals epsilon naught E plus P, which P is the electric polarization in a dielectric medium. Here we have the magnetic polarization. Okay. Well, for most materials, again, that we are going to look at, this magnetic polarization is going to be 0. So B is simply going to be mu naught times H. So everywhere that we see H, we can replace by B divided by mu naught and solve the equation. Okay, what's your question, Edward?
I said, is this just a result of the complex susceptibility? Where we just do a counter integral in Kramer-Kronig relations?
Well, Kramer-Kronig relations are valid no matter what, but this is just an approximation for the types of materials that we are going to consider in this course. Okay. Yeah, I guess ultimately you can say that comes from linear response theory of using the Kramer-Kronig relations. Yeah. Okay. All right. So in such types of medium, let's only look at those medium which are isotropic and homogeneous and linear. So we have to be very, but as we said, there are very broad classes of materials where this is true. Okay. In these materials, also we're going to assume that there are no charges or currents in the material. There might be a distant source of charge, for example, or current, which is giving rise to an electromagnetic wave, but in the volume that we are looking at, or in the area that we are considering these materials, there are no free charges or currents. The light or whatever has been generated in some other place and is coming and is now propagating in this medium. Okay. So we can think of those as boundary conditions. Somewhere far away at the boundary, which is infinitely far away in this situation, there is some charge, there is some current that's giving rise to an electromagnetic wave. Okay. But where we are looking at it, there's no free charge, there's no free current. Okay. And we can simplify Maxwell's equations. So remember in Maxwell's equations, rho and J entered in the divergence equation for the electric displacement. Del dot D equals rho. So if rho is 0, del dot D is also 0, which makes it very symmetric with del dot B equal to 0. So that those two divergence equations are basically very symmetric. And similarly, if J equal to 0, then the two curved equations also look very symmetric, because one is del cross E equals minus dou B over dou T, and the other is del cross H is going to be dou D over dou T. So again, those are going to look very symmetric with respect to each other. So we're going to take advantage of that symmetry. So we're going to take, del cross E equals minus dou B over dou T. I'm going to take one more curve of that equation. Okay. So, and when I do that, when I take the curve of the right-hand side, I move the curl inside the time derivative. And because B equals mu H by the approximation that I just made, it should be mu naught H, but mu H is also fine. B equals mu H over here, which means I can take the mu out and I'm left with this term minus mu dou over dou T del cross H. But del cross H from the Ampere's law is simply dou D over dou T. Therefore, del cross H is dou D over dou T. I get minus mu dou squared D over dou T squared. And D again, remember, is just epsilon times E. So I substitute D equals epsilon E. And before I do that, the left-hand side, which is this del cross E, I use a vector identity. Okay. Sorry, there should be no minus sign. This is gradient of a divergence. Okay. So remember, divergence of an electric wave of a vector field gives me a scalar field, and that I can take a divergence of that. Okay. Minus del squared of E. So this term is also a vector because it's the divergence of some vector field. It's a Laplacian of a vector field. So overall, this is equal to 0 again by the divergence equation. The divergence equation says del dot T equal to 0, and del dot D equal to 0 is equivalent to saying del dot E equal to 0 because I just bring out the epsilon for D. T equals epsilon times E. So this term basically goes to 0. Okay. So the last part, basically, as I said, follows from Gauss's law. So that gives me minus del squared times E. And that gives me finally substituting this back here and equating it to that. And of course, D equals mu times epsilon times E. So I bring out the epsilon. I'm left with del squared E equals mu epsilon dou squared E over dou T squared. Similarly, we can also show that del squared B equals mu epsilon dou squared B over dou T squared. Now, this equation, in case you've forgotten, back when in week 2 or so, when we introduced the wave equation for a single field, a scalar field or a scalar displacement, we showed that the most general plane wave or planar wave equation, wave equation in 3 dimensions must satisfy del squared, say psi, where we chose psi as the scalar field, is equal to some 1 over v squared, the velocity, times dou squared psi by dou T squared. So I know this is a while ago, but if you look back at your notes or at the slides, you'll see that it's del squared psi was 1 over v squared dou squared psi by dou T squared. So we see that we have now derived a wave equation for electromagnetic fields from Maxwell's equations, which is kind of amazing when you think about it, because Maxwell's equations were derived all using things like, let's find out what happens when 2 charges come near each other. So, or let's find out what happens when I change the magnetic field through some circuit. Or let's find out what happens when I take a capacitor and I move the dielectric in and out of that capacitor. Or I change the current going through the capacitor, for example. These were the experiments from which those Maxwell equations were derived. But from that, we have shown that must imply that in a field-free region, these electric and magnetic fields follow a wave equation. Okay, so there must be waves associated with every experiment where you have some time-varying electric and magnetic fields. Okay. Okay, so that gives us then the consequence is that there are 6 wave equations, of course, because the wave equation that I wrote down was in vector format. Okay, so that means I must write it down for each individual component: Ex, Ey, Ez, Vx, Vy, Vc. Okay, so that's 6 wave equations. And as I said, it's introduced, if we set the velocity equal to that 1 over root square root mu over mu epsilon. If I just go back, I can't do it. What? Oh, shit. Here, okay. Right. So, as I said, 1 over v squared must be equal to mu times epsilon, which means v must be equal to 1 over square root mu epsilon. Okay. So we've identified the velocity with which these electromagnetic waves propagate. Again, the properties that we have used to predict that velocity are things that we can measure for a material using experiments with like capacitors and inductors and things like that to calculate the permeability or the permittivity of those materials. Okay, so that's pretty cool. And for vacuum, which was measured, the vacuum permittivity, again using experiments with like capacitors and inductors, you can measure these things, the vacuum permittivity and the vacuum permeability. We get then V, which is the velocity of electromagnetic waves in a vacuum, 1 over square root mu naught epsilon naught. Substitute these values in, you get approximately 3 times 10 to the 8 meter per second, which is the speed of light. Okay, so this is of course Maxwell's great synthesis, the great achievement to show that electromagnetic waves must propagate at the speed of light, and therefore the suggestion then is light is an electromagnetic wave, which wasn't known until then, right? Light must therefore also be an electromagnetic wave. Okay. Okay, so, and that of course has later been shown in many different ways. Okay, so all of this I just set up as our background to show that electromagnetic waves follow a wave equation, or light follows a wave equation, which is the equation derived from Maxwell's equations, and that of course is the Maxwell's wave equation that we just showed a couple slides ago. And further, that it must propagate with this velocity, which can be derived from like very static properties of the material using things like permittivity and permeability. Okay, so that sort of concludes my quick tour of like Maxwell's equations. Any questions before I move on to consequences of the Maxwell wave equation? Yeah.
Could you explain what mu is exactly?
Okay, so the idea is that there are materials that we know which are magnetic. Okay, so in these materials, when you run a current, the total field that you get is actually much higher than you would get from just running the current around that material, for example. Or another way to say that is if I apply a magnetic field to them, they line up. There are like some magnetic dipoles or something inside them that line up and boost sort of the magnetic field that you can achieve in those materials. Now, that's like a ferromagnetic material. But in general, it turns out that every material, when depending on the current or the magnetic field that is applied to the material, will have some response. The field inside the material will not be the same as the field outside the material. That the difference between the field inside the material and the field outside the material, we call this mu, basically. We say the total field B equals mu times H, where H is what is caused by the external current, for example. It's the same idea as like what's the difference between D, the electric displacement, and E, the electric field vector. You think of E as being caused by a charge, a free charge, and D as the field that's inside a material. Okay, and there the field that's inside the material is the sum of the field from outside caused by free charges plus some thing that's going on inside the material, which we call the dielectric polarization P. Same way, M, which I quickly went over, is the magnetic polarization. Okay, and that gives rise to a different magnetic field inside the material than there is outside the material. Does that answer your question? Make sense? Okay. Okay, if there are no other questions, again, I won't expect you to know all this vector calculus for this course, so you don't have to know it. You don't have to be able to manipulate it or anything like that. You do need to know the Maxwell wave equation, the wave equations that we derived at the very end. You should understand that that's how electromagnetic waves follow, because that has consequences for the waves and for optics. But other than that, you don't need to really know how to derive the Maxwell equation, or you don't need to know the Stokes theorem or the divergence. But I hope by now you all had some exposure to those things so that you can understand and follow along these derivations. Okay. All right. So one of the consequences of the Maxwell equations is that this K, E, and V form a right-handed triad in electromagnetic wave. So I'll derive that now. Okay. So now to derive this, it's easiest if I just simply assume something very simple and show you the consequence rather than trying to derive the most general case. You can show it for the most general case, but it's easier if I just show it to you for a simple case like a plane wave. Okay. And you can trust me, hopefully, that it's also true in the most general case. Okay. So assume a plane wave with arbitrary time dependence in all the amplitudes. So what I mean is, of course, a plane wave, as we have seen, is just sine k dot r minus omega t times some amplitude a naught. That was for a scalar. Now for a vector, we know that the vector must have ex. Sorry, just the order of this got messed up. Okay, sorry. So this is the electric field. Okay, the electric field that I'm assuming is a plane wave, which is the cosine k dot r minus omega t that we introduced way back at the beginning. And then, of course, in front of it, we can have three different components: x hat of Vx of t plus y hat Ey of t plus z hat Ez of t. Okay, and it's a plane wave, so we don't include any more dependence on x and y in the amplitude. We assume that at a given plane, that amplitude is a constant. So meaning it may have some different direction and some amplitude, but on that entire plane, it's the same direction and the same amplitude in that one plane. Okay, so that's what a plane wave is. Okay, now we use the divergence equation. Okay, del dot E equals 0. Remember, we are in a region where there are no charges, so del dot E must be equal to 0. Well, immediately you can derive. Remember, divergence is just dou over dou x plus dou over dou y plus dou over dou z. So I just add all those terms: kx ex times sine k dot r minus omega t plus ky ey sine k dot r minus omega t, kz ez times sine k dot r minus omega. So if that has to be equal to 0 everywhere to satisfy the divergence equation, that immediately gives us k dot E equals 0. So we see k and E must always be perpendicular to each other. Okay. So let's, for simplicity, again, as I said, I can show this for the most general situation, but again, to make the map very simple, let's just pick k to be along the z direction, and then E will be, say, along the x-axis to be perpendicular to k. Okay. So then I apply Faraday's law. Del cross E equals minus dou B over dou T. Okay, you can convince yourself that the only term on the left-hand side, since E is only along the x-axis, the only term that survives is this dou Ex over dou Z. Okay. Also because k must be along the z direction, so the only spatial dependence is kz minus omega t. So there's no other spatial dependence. So all the other derivatives are 0 with respect to x or y, etc. So the only term that's left on the left-hand side is dou Ex over dou Z, and that's the y component of that curl equation. So because it's the y component of the curl equation, on the right-hand side, I equate that to dou By over dou T. Okay. Again, you have to carry out the curl, so we won't go through all that math. But since only the y component survives, already we have shown that basically k, E, and V form a right-handed triad, because E is along the x direction, V is along the y direction, and k is along the z axis. Okay. So if I can carry out that integral, and that's shown over here, okay? So, and in fact, in a minute, we will derive the exact formula for B when this is the case, but you can see K is along this axis over here, and E must be perpendicular to that along the x-axis. So I'm showing it, sort of perpendicular to the along. So it must always be in that XZ plane. Okay, so that's X. So that's the XZ plane, and then the YZ plane will be coming out of the board, basically. Okay, and I'll show you in a minute. And as I've just said, B is therefore along the YZ plane, so it's kind of like pointing in and out towards you as it's oscillating along the Z-axis. Okay, so it looks like that. I know it's a little hard to visualize, but this is the best thing we can do. So there's, this is the axis along which the B direction will be, and the X, the E, the electric field will be along the plane, in the plane of the screen or the paper. And of course, K is along the Z direction. Another way to kind of maybe visualize is that if I tilt it a little bit, this whole setup, so that it's not along that way, but Z is sort of pointing like this, that maybe makes it a little bit more clear that E is, say, along the x-axis and B is along the y-axis in the plane, in this plane over here, this plane being the XY plane, basically. Parallel to the XY. Okay, now as I said, we can carry out this integral over here. It's just we just integrate with respect to time, okay, and we calculate what dou Ex over dou Z must be. Again, because it's Ex is simply cosine Kz minus omega t. Dou Ex over dou Z will pull out a K, and then when I do the integral with respect to time, I will take I'll bring an omega down in the denominator, so I get E naught x K divided by omega cosine Kz minus omega t. So if I equate sort of the amplitude, or if I just said, well, if the electric field is E naught cosine Kz minus omega t, then this is just simply, there might be, the minus signs might have been removed. Sorry, there was a little mistake because there's a minus sign from the omega. Okay? So this should be plus. All right. Anyway, so Bz is equal to Ex divided by C. Or you can say that the amplitude B naught Z is simply the amplitude E naught X divided by C, because you can substitute, right? K is 2 pi over lambda, omega is 2 pi F. If you put that in, 2 pi's cancel, you get 1 divided by lambda times F in the denominator. That's just C, the velocity of light in the medium, okay? Or V if it's in a medium that's not vacuum. Okay? I wrote it as C, but it could also have been just V, velocity in the medium. Okay, so that has given us actually an explanation as well for why the magnetic field in an electromagnetic wave is so much weaker than the electric field. Okay, we see now that the electric field amplitude is divided by a number which is extremely large. So if I take a typical electric field, like a couple volts per meter, then the C, the denominator is 3 times 10 to the 8. So your magnetic field is going to be like 10 to the 8 times weaker than the value of the electric field. Okay, which would be fine if, for example, our eyes could respond to the magnetic field with like a magnetic charge, but we can't. We don't have like magnetic charges in our eye that will go up and down. If there's a magnetic field, we are more responsive to the electric field, and the electric field is also larger in these waves, in numerical magnitude, so to speak, relative to the magnetic field. Okay, so okay, I have a couple more minutes, so let me just talk very briefly about polarization of light. Any questions about this slide? And does this sort of picture make sense for K, E, and B, this triad? It can be a little hard to visualize, but it's very important to start visualizing this, because the vector nature of light, this vector polarization of light is very important for many phenomena. So let me just quickly introduce what I mean by polarization of light. Unfortunately, we picked this word polarization, which I know we've already overused. Okay, we used polarization when we talked about dielectrics, talked about polarization when we talked about magnetic polarization, and now we're talking about light's polarization. Okay, so the idea is that, as I said, light is a transverse electromagnetic wave. So the vector nature of this light and the phase relationship between the different components So the way I wrote it was E, which is shown here. Essentially, the idea is very simple. I picked E to be along the x-axis. But what? It can be anywhere, right? As long as it satisfies the relation that k dot E equal to 0, that it's transverse to the k vector, it is fine. It satisfies that relationship. It's anywhere in this transverse plane. If it's anywhere in this transverse plane, that's a permitted state of light. So where this vector E is pointing defines a state for light that we need to know. Okay? That defines an additional degree of freedom, if you like, for the light that we need to specify when we specify a light beam. Okay? And so to specify that, of course, I selected it along the x-axis, but it could have been anywhere in that xy plane. And that's basically all that polarization is, with the additional slight wrinkle that we have time dependence as well. Okay, so sorry. First, so we have time dependence. So the x component of E can be written as some amplitude E naught x cosine kz minus omega t, and then y, which is the y component of the electric field, is the same thing, except I could have an additional phase, epsilon. Okay, that's the most general state of light that I can write down, okay, for the vector. And what I'll show you in the next class is that for certain epsilon, because of the minus sign in this omega t, when epsilon is greater than 0, the y component will lag behind. Because basically, because of the negative sign in omega t, the way we chose the original wave, this means that when epsilon is greater than 0, that we have to wait an additional time t until the two are equal to each other. So Ey will lag behind the Ex if epsilon greater than 0 with this choice of that kz minus omega t. There are books in which you'll find that people have chosen the opposite convention. They say it's omega t minus kz. Okay, I hate that convention, but there are books where they choose cosine omega t minus kz, which is allowed because, as you know, a wave just has to be of the form x minus vt. Okay, so you can choose that as omega t minus x or x minus vt. Okay, so I like this convention, and this is the convention in your book, so we'll follow that convention. And when you do that, then a positive epsilon over here means the y component will always lag behind the x. Okay, so I'm going to stop there, and we'll continue onwards from the next one.
So to be ready